Hello, Chem students. Today we're going to learn about stoichiometry and percent yield. So this is just continuing on what we've learned from stoichiometry. We're just going to learn some new concepts and go a little deeper into this topic. So a couple different things we need to understand. Predicted yield. That's the first thing. So predicted yield is the expected quantity of a product based on calculations. So this is what you've been doing so far. You've been calculating and figuring out what your predicted yield is based on stoichiometry. All right. So this is what we're doing so far. Experimental yield is what happens when you do a lab. When you do a lab, you're going to do measurements. You're going to weigh your products on a scale, and you're going to see what you actually got as an experiment. So the quantity of a product actually obtained during a reaction, also called actual yield, this is your lab. So factors that affect experimental yield. Why do we do this? Why don't we always just get 100% reaction? Because, well, life isn't perfect. So some factors that affect yield. So competing reactions. Sometimes there's reactants can perform two or more reactions that compete with each other. So even though we don't notice it, sometimes there's reactions that happen in the background that aren't part of what we're assessing. And sometimes that happens, I've seen it before, where you have bubbles being produced, but in your reaction, there's no gas being produced. So that's one example. So for another example, hydrogen and oxygen can react to produce water or hydrogen peroxide. Both of these are going to compete with each other in terms of what is going to be our final product. Next one, slow reactants. If the reaction is slow and not enough time has been given to the experiment, the experiments will yield maybe less than predicted. So sometimes things take a long time. If you don't wait long enough, you try and quickly do the lab and rush through things, you're not going to get as much yield as you should. Third one, collection and transfer method. So sometimes you spill a little, or you make some mistakes, or drop some of the precipitate that you're collecting. That's another one. Third one, reactive purity. We generally order pretty good quality stuff at our school, but for the most part, it's hard to get reactants that are 100% pure. So if there's other compounds there, they might add to your mass, but they're not actually going to be part of the reaction and give you the product that you're looking for. Last one, reactants that do not proceed to completion. So some reactions reach a point where they appear to stop even though 100% of the reaction has not been used. This is because the reactants has reached equilibrium, which is something that you'll learn about next year in Chem 30. So 100% reaction, not always a very common thing. To go back to this slow reaction, one thing you can do to do this is add energy. So some examples of energy, you got kinetic energy or stirring, or you got thermal energy, which is heat. Both of these will speed up the reaction. So those are a couple reasons of why you're going to have experimental yields being less than what your calculated yield is. So make sure you know these different reasons, and they will be referred to on some quizzes and such. So let's go through an example. When heated, calcium carbonate decomposes into solid calcium oxide and carbon dioxide gas. If 24.8 grams of calcium carbonate are heated and 13.1 grams of calcium oxide are collected, what is the first one? We're going to do predicted yield of calcium oxide, and then we're going to do the percent yield. So just like any Stoic question, we're going to write out our formula of what we're looking at. We've got calcium carbonate is what we are dealing with here. And what happens to it is it will decompose into calcium oxide and carbon dioxide. All that's given to us right here in this formula or in the question. Next thing give us if 24.8 grams, so we have a mass. As soon as you have mass, you need molar mass. And we got a mass of calcium oxide, which is 13.1 grams. So how we have to differentiate and look at these is it's saying in an experiment, you produce this much calcium oxide. But what we need to do is understand that this is an experiment. It's not in a theoretical part like our stoichiometry calculation. So what we have to do is figure out, well, what mass theoretically should we get from decomposing calcium carbonate? So that's what we're looking for. Mass and molar mass of calcium oxide. So last thing we got to do is just check our balancing. We got one calcium, we got one carbonate, we got one oxygen, three oxygen, three oxygen. We're balanced already. We're all good. So we are just going to go through this and do a basic stoichiometry. First step, we're going to do a step-by-step method here. Step number one, well, find the moles of the given. Mass over molar mass. We've got 24.8 grams divided by 100.09 grams per mole. We're going to have the moles of the given to be equal to 0.24777 moles, and that's calcium carbonate. So first step, find the moles of the given. Step number two, mole ratio. So we have moles of what we know. We need to find the moles of our unknown. And that's the moles of calcium oxide. So we start with what we know, calcium carbonate, times our mole ratio, and we have 1 mole of calcium oxide for every 1 mole of calcium carbonate. And that is going to give us our moles of calcium oxide to be the exact same thing. Nice. And 1 mole ratios are always nice, but we have to do the math to make sure and show this. And then step 3 is solving for what we know. So we are looking for the mass of calcium oxide. So we're going to take this value for finding that. Take this value, put it up here, and we have 0.24777 moles times by our molar mass. And our moles cancel out. We do our math, and we get a mass of 13.895 grams, or if we want to do, we got to do our sig digs. 13.9 grams of calcium oxide. So theoretically, this is how much we get. And if we look at what's given in our experiment or in the lab, we got 13.1 grams in the lab. So now we want to calculate our percent yield. We have to figure out how effective this lab was or this procedure was to get what we're looking for. So here's our formula up here. Percent yield equals experimental yield over predicted yield times 100. So this is the same way you calculate your percentage from class. You do how many you got right over how many questions there were on the test times 100 gives you what the percentage was you got on the test. So our percent yield, we do our experimental over our predicted times 100%. We put our values in, we get 13.1 grams divided by 13.9 grams. That's our predicted from our calculations. And we're going to times that times 100%. 13.1 divided by 13.9. We get our percent yield to be equal to 94.2%. And that's our final answer. We got 94.2% yield. That's pretty good. That's like getting 94% on a test. How to make sure you get this right is make sure you're carrying your digits all the way through. And then if you can do your calculations, try and use as much digits as you can. Okay. And yeah, that's how you get your percent yield for a calculation.